Imagine standing in sunlight so strong it can burn metal, while the shadow beside your hand is cold enough to kill a machine. That is one of the strangest truths about space. The sun can flood a spacecraft with heat, light, ultraviolet radiation, and charged particles. Yet the same spacecraft can lose warmth into blackness at the same time. One side may become dangerously hot. The other side may fall into a cold so deep that fuel lines, batteries, joints, cameras, and human skin all need protection. That is why the question is not as simple as it sounds. If the sun is so hot, why can space still freeze you? Before we begin, if you enjoy slow space documentaries like this, subscribe to the channel, leave a like, and write a comment telling us where you are watching from and what time it is for you right now. It is always strange to imagine people hearing the same story from different places on Earth, under different skies, at different hours of the night. Tonight, you are watching the Space for Sleep channel, talking about why space can freeze you even near the sun. And the first thing to understand is that space does not behave like a cold winter night on Earth. On Earth, cold feels like something touching you. Cold air moves across your face. Wind pulls heat away from your skin. Snow touches your gloves. Ice draws warmth out of your fingers. A metal bench on a winter morning feels colder than the wood beside it, because it moves heat away faster. Even when you are standing still, air is always carrying energy from one place to another. That is the ordinary version of cold we know. But space does not have enough air for that. There is no thick atmosphere pressing against you. There is no wind in the everyday sense. There is no ocean of gas surrounding your body. No room temperature air touching your suit. No blanket of molecules waiting to share heat. In most of space, there is almost nothing close enough to bump into you. That makes temperature more confusing. A thermometer on Earth measures the motion of particles around it. In a room, those particles are air molecules. In a pot of boiling water, they are water molecules. In a freezer, they are slower-moving molecules that still exist in great numbers. But in the vacuum between planets, there may be so few particles that a normal idea of air temperature stops being useful. Space is not cold because it is filled with freezing air. Space feels cold because empty space gives your heat almost nowhere to come from. And one main way to leave: radiation. Everything warm glows, even if your eyes cannot see it. A human body glows in infrared. A spacecraft glows in infrared. A warm rock on the moon glows in infrared after sunset. The warmer something is, the more energy it sends away as radiation. On Earth, radiation is only part of the story, because air, water, ground, clothing, clouds, and walls also move heat around. In space, radiation becomes the main path between an object and the universe around it. This is why the same place can be both burning and freezing. If sunlight hits you directly, energy pours in. If you face deep space without enough incoming energy, energy leaks away. If one side receives the sun while the other side faces darkness, the two sides may not agree at all. A spacecraft is not simply hot or cold, it is a battlefield. The sun is attacking one surface, black space is draining another. Electronics inside are generating their own heat. Fuel tanks need to avoid freezing. Batteries need to stay within a narrow range. Cameras may need to be cooled. Human cabins need to stay comfortable. Radiators must release waste heat without losing too much. Insulation must slow the escape. Heaters must turn on when a component falls too far. Thermal control is not a small detail. It is one of the reasons a machine can survive long enough to do anything in space. The strange part is that this is true even near the sun. Near the sun, the problem is not that space stops being cold. The problem is that space stops being simple. A metal plate facing the sun can grow dangerously hot. Turn the same plate away, give it a clear view of black sky, and it begins radiating energy away. If it is poorly designed, it may cool too far. If it is shaded behind a heat shield, it may need heaters while only a small distance away another surface is being scorched. This is not a contradiction. It is the reality of vacuum. Heat does not fill space the way warmth fills a room. The sun sends energy through space, but that energy does not warm the vacuum itself in the same ordinary way sunlight warms air and ground on Earth. Sunlight travels across the emptiness until it hits something. A planet, a dust grain, a spacecraft, a spacesuit, a solar panel, a human eye. Only then does the energy become part of that object's thermal problem. So, if you ask how cold space is near the sun, the honest answer is, it depends on what you are made of, where you are pointing, how reflective you are, how fast you can radiate heat, and whether anything is blocking the light. A black surface and a white surface in the same orbit can reach different temperatures. A thin antenna and a thick fuel tank can respond differently. A rotating spacecraft and a fixed spacecraft can live in different thermal worlds. A human in direct sunlight and a human in shadow are not in the same environment, even if they are only a few meters apart. That is the first terrifying part. Space does not give you one temperature to survive. It gives you extremes at the same time. One of the clearest places to see this is not near Mercury or the Sun, but on the Moon. The Moon is close. It is familiar. We see it almost every night. It has been visited by humans. It looks calm from Earth, pale and silent, like a soft object hanging above the horizon. But the surface of the Moon is a brutal demonstration of what happens when there is sunlight without a thick atmosphere. During the lunar day, the surface can become extremely hot. During the lunar night, it can become extremely cold. There is no ocean to store and move heat, no thick blanket of air to smooth out the difference, no weather system to soften the boundary. The ground bakes under sunlight, then radiates its energy away into blackness when the sun disappears. The Moon is not far from the Sun compared to Earth. It sits in roughly the same neighborhood of the solar system. Yet without an atmosphere like ours, its surface swings between deadly states. That should immediately break the simple idea that being near the Sun means being comfortably warm. The Moon receives strong sunlight, but it can still become violently cold in darkness. Now imagine a future astronaut walking near the rim of a lunar crater. The sun hangs low over the horizon. The landscape is bright in one direction and pitch black in another. A rock in sunlight may be hot enough to stress equipment. A shadow inside a nearby crater may be cold enough to preserve ice for billions of years. The astronaut steps beside a place where sunlight has not reached for ages, and the difference is not like shade under a tree. It is a thermal cliff. The same solar system, the same moon, the same moment. Heat on one side, ancient cold on the other. This is why engineers care so much about shadows. On Earth, a shadow is usually cooler, but still surrounded by air. Heat can flow in from nearby ground. Warm wind can pass through. Infrared radiation from clouds and buildings still reaches you. On the Moon, a shadow can be almost a different world. A permanently shadowed region near the lunar poles may stay extremely cold because sunlight never climbs high enough to reach its floor. Heat must arrive by weaker paths. Scattered light, radiation from nearby terrain, conduction through the ground, or impacts and other small sources. If those sources are limited, the cold remains. That is why water ice can hide in dark lunar craters. The sun is not absent from the solar system. It is simply blocked from that place. This matters because the same principle appears again and again across space exploration. A spacecraft does not only ask how far it is from the sun, it asks what parts are illuminated, what parts are shaded, what surfaces can radiate to space, and what materials connect the hot side to the cold side. A solar panel may want sunlight. A fuel line may hate it. A camera detector may need cooling. A battery may need warmth. A human cabin may need both, depending on the hour. If you have ever looked at a spacecraft and wondered why it is wrapped in gold, silver, black blankets, white panels, radiator grids, pipes, vents, and reflective coatings, the answer is partly this problem. It is not decoration. It is survival. Engineers are trying to decide which parts should absorb sunlight, which should reflect it, which should trap heat, and which should throw heat away into space. That sounds technical, but the human version is simple. In space, your warmth is not protected by the environment. It is protected by a system. The moment that system fails, the universe does not help. A spacesuit is not only a small pressure vessel, it is also a thermal machine. It has to keep the astronaut from overheating while working in sunlight and from cooling too far in shadow. Inside the suit, the body produces heat constantly. Muscles work, blood moves, electronics run. The suit must remove excess heat. Otherwise, the astronaut can overheat even in space. But the suit also has to prevent uncontrolled heat loss, especially when the astronaut is not in the sun or when the environment drains energy from exposed parts. That is why the phrase, "space can freeze you," needs care. You would not instantly become a block of ice the moment you entered vacuum. Movies often make space look like a magical freezer that turns people solid in a second. Reality is stranger and more dangerous. The vacuum would cause other problems first: loss of pressure, inability to breathe, swelling of exposed tissues, water at surfaces behaving differently, and unconsciousness from lack of oxygen. But after the immediate pressure and oxygen emergency, thermal balance still matters. Your body radiates heat away. Moisture can evaporate, carrying energy with it. Without protection, you cannot control the process. The danger is not just cold. It is the loss of normal physics your body was built for. You were not designed to be a warm object, facing a vacuum and a star. You were designed to live inside a thin layer of air, on a planet with oceans, clouds, soil, and a sky that returns some heat back down. Space removes most of that support. It leaves your body and machines to solve heat transfer directly. This is why cold in space can feel misleading. A person can overheat in a spacesuit, while space itself has almost no air to feel warm. A spacecraft can carry heaters because parts of it freeze, while other parts need radiators. A probe can fly close to the sun and still hide its instruments behind a heat shield in a cool shadow. A telescope can be placed far from Earth and protected from sunlight so its instruments become cold enough to detect faint infrared light. Cold and heat are not enemies in space. They are often present together. The nightmare is controlling which one reaches which part. To understand the problem more clearly, imagine a simple object drifting in space, a small metal sphere near Earth's orbit. At first, let it sit in direct sunlight. Photons from the sun strike its surface. Some are reflected, some are absorbed. The absorbed energy warms the metal. As the sphere warms, it begins radiating infrared energy in all directions. Eventually, if nothing changes, it may reach a balance. Energy arriving equals energy leaving. That balanced temperature depends on the object's color, reflectivity, shape, rotation, thermal conductivity, and internal heat. Now move the same sphere into shadow. The incoming sunlight drops away, but the sphere still radiates infrared energy. Energy leaves. Little arrives. Its temperature falls. It does not need cold air touching it. It cools because it shines its heat into space. That one example explains countless spacecraft problems. But real spacecraft are more complicated than metal spheres. They have flat panels, booms, tanks, computers, cameras, engines, joints, wires, insulation blankets, moving arms, windows, mirrors, antennas, batteries, and sometimes human beings. Each part has a different temperature limit. One instrument may fail if too warm. Another may fail if too cold. A battery may lose capacity. A lubricant may thicken. A seal may become brittle. A pipe may freeze. A computer may overheat. A solar panel may produce power but also absorb heat. A radiator may work beautifully until the spacecraft points the wrong way. So thermal control becomes choreography. A spacecraft must point itself not only for communication, science, or propulsion, but for temperature. It may rotate slowly to spread sunlight across its body. It may hide sensitive instruments behind shields. It may use louvers that open and close like mechanical eyelids. It may pump heat from one region to another. It may use multi-layer insulation to slow radiation. It may switch on small electric heaters, not because space is warm, but because space is too good at taking heat away from exposed surfaces. This is the opposite of what many people expect. We imagine the sun as the main danger near the inner solar system, and it is. But the shadow of the sun can also be dangerous. A spacecraft near Earth can enter eclipse behind the planet. One moment it is being illuminated, then it passes into Earth's shadow. Solar power drops. Surfaces stop receiving sunlight. Temperatures shift. Later it comes back into sunlight, and everything changes again. The spacecraft must survive these cycles over and over. Low Earth orbit is not gentle. It is a rapid alternation between sunlight and darkness, heat input and radiative cooling, power generation and battery drain. The International Space Station has enormous thermal systems because humans and machines produce heat, sunlight adds heat, shadow removes heat, and the crew needs a stable environment inside. Outside, large radiators release waste heat into space. Inside, pumps and loops move thermal energy away from equipment. Without those systems, a station full of people and electronics would not simply remain comfortable because space is cold. Some parts would overheat, others would become too cold. The station survives because it manages heat deliberately. That word matters. Manage. Space does not automatically cool everything in a useful way. It cools whatever can radiate to it. It heats whatever absorbs sunlight. It gives almost no help through air. This is why a spacecraft can die from cold even while sunlight is nearby. A component tucked behind a panel may have a poor view of the sun. It may be thermally isolated from warm equipment. It may radiate energy through a small exposed surface. If the heater fails, the component can fall below its survival temperature. A fuel tank placed too far from internal heat may need dedicated warming. A rover on a planet or moon may survive the day, then struggle through night. A lander that cannot produce or store enough heat after sunset may freeze from the inside. On Mars, the atmosphere is thin, but not absent. It still moves some heat, carries dust, and creates weather. Yet spacecraft on Mars still face brutal cold. Rovers need heaters. Electronics need thermal protection. Batteries are carefully managed. The ground and air change with the day. Dust can affect sunlight. The temperature cycle can stress materials. Mars is farther from the sun than Earth, so less sunlight arrives. But the lesson remains similar. Exploration is often a fight against thermal extremes, not a simple fight against one temperature. Go farther out, and the problem changes again. At Jupiter, sunlight is much weaker than at Earth. At Saturn, weaker still. In the outer solar system, solar panels become less useful and less enormous, and spacecraft often depend on nuclear power sources that produce heat as well as electricity. That heat is not just useful, it can be essential. Deep space probes must keep instruments and systems warm while the sun becomes a bright but distant star. A machine heading outward does not need to be frozen by cold air. It simply receives less and less energy from the sun. while it continues to radiate heat into space. If it cannot replace what it loses, it cools. This is why deep space exploration is an energy story. A probe does not only need fuel to move or electricity to transmit, it needs thermal survival. It needs enough warmth to keep critical parts alive. A radioisotope power source is valuable partly because it provides a steady flow of energy in a region where sunlight becomes weak. Some of that energy becomes electricity, some becomes heat. In the deep dark, waste heat can become a gift. There is something almost beautiful about that. The same heat that is a problem near Earth becomes a lifeline far from the sun. Near the sun, engineers ask how to reject energy. Far from the sun, they ask how to keep it. Between those extremes, spacecraft live by balance. The sun itself deepens the mystery because it is not only hot, it is enormous. Its surface is thousands of degrees. Its corona is far hotter. It sends radiation across the solar system. It drives the solar wind. It creates storms that can damage electronics and threaten astronauts. Yet the space around it is still vacuum. The energy is moving through emptiness, not warming a thick cosmic atmosphere. That is why NASA's Parker Solar Probe can fly close to the sun only by using a carefully designed heat shield. The spacecraft is not simply sitting in a hot room. It is moving through intense sunlight and a harsh solar environment. Its shield faces the sun, absorbing and reflecting extreme energy while keeping many instruments in shadow. Behind the shield, the spacecraft can remain within survivable temperatures. This is one of the most dramatic examples of the difference between sunlight and air temperature. A shield only a short distance across can separate a sun-facing inferno from a protected region that is much cooler. If space were like an oven filled with hot air, that would not work in the same way. Hot air would wrap around the shield. Convection would carry heat behind it. But in the near vacuum of space, blocking radiation matters enormously. Orientation matters. A shadow can save a spacecraft even while it is passing closer to the sun than any previous mission. That is both brilliant and unsettling. It means a spacecraft near the sun survives by keeping the sun in exactly the right direction. If it points incorrectly, the wrong parts can be exposed. A heat shield can no longer protect what it was meant to protect. Instruments can be damaged. Systems can fail. Near the sun, a mistake in attitude control can become a thermal disaster. Farther from the sun, a different pointing mistake can be fatal for the opposite reason. A spacecraft may need to keep solar panels illuminated to generate power. It may need to keep an antenna facing Earth. It may need to keep radiators away from the sun. It may need to keep instruments shaded. These needs can compete. A machine cannot always point everything exactly where every system wants. Mission design becomes a puzzle of light, heat, power, communication, and science. This is why space missions are full of thermal constraints that sound invisible to the public. A telescope cannot look too close to the sun. A probe cannot expose certain instruments for too long. A rover may sleep during cold periods. A lander may die when winter drains too much energy. A camera may need warm-up time. A spacecraft may enter safe mode because its temperature or power margins have become dangerous. To viewers on Earth, these are technical details. To the spacecraft, they are survival. Now, return to the human body. Suppose an astronaut is floating in deep space, inside a suit, with sunlight on one side and blackness on the other. The suit must keep pressure in. It must provide oxygen. It must remove carbon dioxide. It must protect against radiation and micrometeoroids. But it must also handle heat. The astronaut's body is constantly generating it. In sunlight, the suit absorbs external energy. During work, the astronaut produces even more. Without cooling, overheating can happen. In shadow, the suit must prevent excessive heat loss. It may need layers that reflect infrared radiation back inward. It may need active systems that move heat where it can be controlled. A spacesuit is therefore not just clothing. It is a small spacecraft shaped like a person. If the cooling system fails during heavy work, space can be deadly without being cold enough. If heating and insulation fail in shadow or during long exposure, space can drain warmth away. If pressure fails, the immediate danger arrives even faster. Every survival system is linked. Heat, air, water, electricity, pressure, and time are not separate in space. They become one problem. This is why simple statements fail. Space is not just cold. Space is not just hot near the sun. Space is exposure. Exposure to radiation without atmosphere. Exposure to darkness without air. Exposure to your own waste heat, with nowhere easy to put it. Exposure to the fact that a warm body must obey physics every second. On Earth, the environment buffers us. In space, engineering replaces the environment. That may be the most important idea in this entire subject. We often talk as if spacecraft are moving through a place, but in a very real sense, they carry a place with them. A spacecraft is a pocket of managed temperature inside unmanaged emptiness. It is a small region where heat has rules, because outside, the rules are too extreme for ordinary life. The cabin of a spacecraft may feel calm. Lights glow, fans hum, laptops run, people sleep in bags attached to walls. A meal warms in a container. A voice speaks over a headset. From the inside, spaceflight may briefly feel like a strange room, but outside that wall, the room ends. One side of the hull may be in sunlight, another may face blackness. A radiator panel may be glowing heat away. A blanket of insulation may be preventing a tank from freezing. A small heater may be protecting a valve. A shadow may be crawling across a surface as the vehicle turns. And all of it must remain within limits. The calm interior exists only because the thermal fight outside is being won. That fight becomes even harder when missions last years. A short mission can carry more margin. It can depend on systems that only need to survive a limited number of cycles. But a long mission must survive aging. Insulation changes, dust collects, coatings darken or degrade, moving parts wear, heaters consume power. Electronics create heat patterns that shift as systems fail or are turned off. A spacecraft on a long journey is not only surviving space, it is surviving time in space. Thermal design must account for what the spacecraft will be years later, not just on launch day. A radiator that worked when clean may behave differently after contamination. A surface that reflected sunlight may absorb more after darkening. A battery that tolerated cold early in the mission may become more fragile with age. A heater that used to be optional may become essential. This is one reason old spacecraft become precious and difficult to manage. They are not frozen statues drifting unchanged. They are aging machines in a relentless environment. Every watt matters. Every temperature margin matters. Operators on Earth may have to turn off instruments, change operating schedules, or adjust pointing to keep the mission alive. Cold in space is not dramatic only when it kills quickly. Sometimes it kills slowly, by narrowing choices. A spacecraft loses power margin. A heater can no longer run as often. An instrument is too cold to operate safely. A battery must be protected. Communication windows shift. The mission becomes less about ambition and more about survival. Eventually, a machine may still be physically intact, but unable to keep itself warm enough to function. That is a quieter kind of freezing, not ice forming on a windshield. A future disappearing from a circuit board. A signal fading because the machine can no longer hold the temperatures it needs. This is also why distance from the sun matters so much. Sunlight weakens with distance. Move twice as far from the sun, and the same area receives only about 1/4 the sunlight. Move 10 times farther, and the sunlight is 100 times weaker. This inverse square relationship shapes the entire solar system. Earth is bright and warm compared with the outer planets because we are close enough to receive abundant solar energy. Jupiter still receives sunlight, but far less. Neptune receives only a tiny fraction of what Earth receives. Out there, the sun is still bright to your eyes, but not generous to a spacecraft. A human standing near Neptune, if such a thing were possible, would not feel sunlight the way we do on Earth. The sun would be a brilliant star, but the energy arriving per square meter would be small. Solar panels would struggle. Thermal systems would lean heavily on internal power. The surrounding darkness would dominate. The body would not be warmed by a friendly day. Machines would need to carry heat as carefully as they carry data. Now push farther, past the planets, toward the outer edge of the solar system. The sun becomes less a source of warmth and more a direction. The background of space remains. The cosmic microwave background, the afterglow of the early universe, fills the cosmos with radiation at only a few degrees above absolute zero. This does not mean every object instantly becomes that temperature, because objects can have internal heat, absorb sunlight, or receive radiation from other sources. But if you place an object far from stars, with no internal power and enough time to radiate away its heat, it tends toward a deep cold. That is what the universe offers by default. A faint bath of ancient radiation, a darkness with almost no warmth. Starlight exists, but it is thin. Cosmic rays exist, but they do not make a comfortable climate. Dust and gas exist, but too sparsely in most places to behave like air. If you remove nearby sunlight and internal energy, the universe is not a room waiting at livable temperature. It is a sink, a place where heat can leave and almost nothing replaces it. This is why rogue planets are so haunting. A rogue planet is a world without a star, drifting through interstellar darkness. If it once had oceans, those oceans may freeze from the top down. Its atmosphere may collapse depending on composition and heat. But deep inside, radioactive decay and leftover planetary heat may continue. Under thick ice, there could be liquid water in some cases. A world can be frozen on the outside and warm enough inside to remain geologically alive. Again, space refuses to be simple. Cold surface, warm interior. Dead sky, hidden ocean. The same physics that threatens a spacecraft may preserve a secret under ice. The universe is full of such contrasts. An asteroid in sunlight can heat during the day and cool sharply at night. A comet far from the sun remains frozen, then awakens when it approaches closer, and sunlight drives gas from its surface. A moon around a giant planet can be far from the sun but warmed inside by tidal forces. A space telescope can use darkness as a tool, deliberately cooling its instruments so they can see faint infrared signals. A planet with a thick atmosphere can trap heat that a bare rock would lose. A tiny dust grain can change temperature quickly. A large world changes slowly. Temperature in space is never just location. It is size, material, sunlight, rotation, atmosphere, internal heat, surface color, geometry, and time. That is why a title like "Why Space Can Freeze You Even Near the Sun" is really about a deeper idea. The universe does not care how close something feels. It cares about energy balance. Near the sun, a protected shadow can be cool. Far from the sun, a radioactive core can stay warm. On the moon, a crater can preserve ice, while nearby ground heats under daylight. Inside a spacecraft, a human can be comfortable, while outside surfaces face lethal extremes. Nothing survives because the environment is kind. It survives because the flow of energy has been controlled. And the moment control fails, the truth returns. The sun is not a blanket, space is not air, a shadow is not merely shade. A spacecraft is not simply in space. It is thermally negotiating with space every second. This negotiation begins before launch. Engineers test hardware in thermal vacuum chambers because ordinary rooms cannot reproduce the real problem. They place spacecraft components in chambers where the air is pumped out. Walls can be heated or cooled, and radiation becomes the main pathway. They simulate sunlight. They simulate darkness. They cycle parts through extremes. They watch what expands, contracts, cracks, leaks, warps, freezes, or overheats. The goal is not just to prove that a machine works. The goal is to prove that it works when the usual ways of moving heat are gone. A screw may loosen because materials expand differently. A lens may shift focus because temperature changes its shape. A tank may change pressure. A seal may leak. A circuit may behave differently. A mirror may distort by a tiny amount that matters for science. A solar panel may flex. A battery may become unsafe. These are not dramatic visuals, but they are the difference between a mission that lasts years and a mission that dies early. Space is full of invisible failure modes. Thermal failure is one of the most unforgiving because it can spread through systems. A cold battery reduces power. Lower power weakens heaters. Weaker heaters make other components colder. A frozen line prevents movement of fluid. A blocked system changes pressure. A computer shutoff changes internal heat. A pointing error exposes a sensitive surface. One issue can become a chain. That is the real horror of space cold. It often arrives as a cascade, not a single icy blast. A sequence of margins vanishing. First a component leaves its safe range, then a backup heater turns on. Then power budget tightens. Then science instruments shut down. Then communication becomes harder. Then the spacecraft must choose between staying warm and doing the mission it was built to do. For humans, the chain can be even more direct. A habitat on the Moon or Mars must handle external cold, internal heat, equipment loads, air circulation, water systems, sleeping areas, food storage, and emergency modes. If the power system fails during a long night, heating becomes critical. If radiators fail during high activity, overheating becomes critical. If a dust storm reduces solar power, thermal management changes. If a coolant loop leaks, the habitat becomes vulnerable. If a door seal fails, pressure and temperature emergencies combine. Living in space is not just about having walls. It is about having walls that can maintain an artificial climate against a universe that does not provide one. Even on Earth, heating and cooling are civilization-level systems. Homes need insulation. Cities need power. Hospitals need climate control. Food needs refrigeration. Computers need cooling. Water pipes need protection from freezing. Now remove the atmosphere, reduce rescue options, and place the entire settlement under a sky that either burns, freezes, irradiates, or ignores you. A space colony is a thermal promise. It promises that inside water will stay liquid, air will stay breathable, food will grow, electronics will work, humans will sleep without freezing or cooking. If that promise fails, the outside does not become forgiving. This is why the future of space settlement depends so much on heat. Not just rockets, not just courage. Heat, where it comes from, where it goes, how it is stored, how it is moved, how it is rejected, how it is conserved, how it is controlled when something breaks. A lunar base near the South Pole might seek sunlight from high ridges and water ice in shadowed craters, but those two resources are separated by thermal extremes. A Mars base might use buried habitats to smooth temperature swings. A deep space vessel might use reactors, radiators, insulation, and rotating thermal schedules. A telescope might hide behind a sunshield to become cold enough to see the early universe. A probe near the sun might keep its instruments alive by never letting the sun see them directly. Every mission is an answer to the same question. How do we keep the right things warm and the right things cold? That sounds simple until you realize the answer must work for years, sometimes decades, without a repair shop nearby. A car radiator can be replaced. A house heater can be serviced. A satellite beyond Mars cannot be reached by a technician. A probe near the sun cannot pull over and cool down. A crew on a distant mission cannot wait for Earth to send help if the thermal system crosses a limit too quickly. This is why engineers build redundancy. They create backups. They add sensors. They model failure cases. They watch temperatures obsessively. A number on a telemetry screen can tell them whether a mission is safe, stressed, or slowly entering danger. To the public, the image may be a beautiful spacecraft over a planet. To the mission team, the story may be a list of temperatures, voltages, currents, pressures, and margins. Space exploration is romantic from far away. Up close, it is maintenance against physics. The cold side of that physics is especially patient. It does not need to attack. It waits for the sun to be blocked. It waits for power to fall. It waits for a heater to fail. It waits for a spacecraft to rotate incorrectly. It waits for the long night. And then it simply lets heat leave. That is why a shadow in space can feel more frightening than darkness on Earth. On Earth, darkness is still full of air. It still carries sounds, smells, humidity, and warmth from nearby places. In space, darkness can be a view into a thermal sink older than Earth. It is not just the absence of light. It is the absence of a surrounding environment that wants you alive. This does not mean space is evil. It means space is indifferent. The sun gives energy. Empty space removes it. Matter responds. Living things must stay within narrow limits. Machines must stay within narrower limits than people imagine. The entire drama comes from that mismatch. The universe operates across extremes, while life occupies a thin thermal band. Earth is special, partly because it hides this from us. Our planet rotates. Our atmosphere moves heat. Oceans store it. Clouds reflect and trap it. Land absorbs and releases it. Greenhouse gases keep the surface warmer than it would otherwise be. Weather spreads energy from equator to pole. Even deserts and polar regions exist within a planetary system that buffers extremes compared with bare rock. We live inside a heat engine. We rarely feel the raw sun and raw space at the same time. A sunrise warms the ground, but the air mediates it. A winter night cools the surface, but the atmosphere slows the loss. Clouds can keep night warmer. Winds can carry heat across continents. Water takes a long time to cool. The planet makes temperature feel continuous. Space removes the continuity. It gives you direct sunlight or direct darkness. It gives you radiation without air. It gives you silence where convection used to be. That is why the first step to understanding space cold is unlearning Earth. A cold day on Earth is not the model. A thermos bottle is closer. A thermos works because it limits heat transfer. It uses vacuum to reduce conduction and convection, and reflective surfaces to reduce radiation. It keeps hot things hot and cold things cold, not because vacuum is cold, but because vacuum prevents easy heat exchange. Space is similar in one way and different in another. It removes air-based heat transfer, but it still allows radiation, so an object in space can keep heat for a while if insulated, or lose it steadily if exposed, or heat rapidly if it absorbs sunlight. Vacuum is not a temperature. Vacuum is a lack of easy contact. That distinction explains why an astronaut might not freeze instantly, why a spacecraft needs radiators, why satellites can overheat, why shadows can become deadly, and why deep space is still associated with cold. Cold in space is not the cold of touching ice. It is the cold of being unable to replace what you radiate away. It is the cold of being separated from a warm environment. It is the cold of having no atmosphere to lend you energy. And near the sun, it can still matter, because the sun's energy is directional. It arrives from one direction, as light. It can be reflected, absorbed, blocked, concentrated, or shaded. If you are protected from it, you can cool. If you are exposed to it, you can overheat. If your system has both exposed and protected parts, you must manage the difference. The Parker Solar Probe is a perfect example again, because its survival depends on not confusing proximity with surrounding warmth. The probe's heat shield faces the sun. Its instruments hide behind it. Solar arrays are carefully managed. Cooling systems help them survive. The spacecraft does not defeat heat by being tough in a general way. It defeats heat by shaping exactly where sunlight is allowed to go. A shadow keeps part of the spacecraft alive, close to the sun. That sentence feels impossible until the physics becomes clear. A shadow can be a shelter because the main incoming heat is radiation. Block the radiation, and you remove the largest direct source. Then the protected systems must handle their own internal heat, and any heat conducted through structures, if designed correctly, they remain survivable. If designed poorly, they may become too hot or too cold. In space, shadow is not just darkness. It is a thermal decision. That is why sunshields are so powerful. The James Webb Space Telescope, for example, uses a vast sunshield to block sunlight, earthlight, and moonlight from its sensitive instruments. Its science requires cold. To see faint infrared light from distant cosmic objects, it must reduce its own thermal glow. If the telescope were warm, it would blind itself in infrared. So Webb does not merely observe cold space. It uses cold as part of the instrument. This reveals another twist. Cold is not always an enemy. Sometimes it is the reason a mission works. Infrared astronomy needs cold detectors. Some instruments must be cooled to incredibly low temperatures. Space helps, but only if the spacecraft is designed to use it correctly. A telescope that can radiate heat away into deep space while blocking sunlight can become far colder than it could on Earth. The same emptiness that threatens astronauts allows scientists to build instruments that hear the faint whispers of the early universe. So the cold of space is both danger and tool. It kills unprotected systems. It preserves ice in shadow. It cools telescopes. It threatens batteries. It reveals faint light. It breaks materials. It makes some science possible. The difference is control. This is why the phrase, "space can freeze you," should not be heard as a simple horror line. It is more interesting than that. Space can freeze you because there is no protective environment balancing your heat. But space can also overheat you because direct sunlight is intense. Space can preserve ancient ice beside sunlit ground. Space can cool a telescope while the telescope sits near Earth. Space can make a probe near the sun survive behind a shield. Space can make a habitat dangerous when power fails, and make a radiator essential when power works too well. The problem is not that space has one personality. The problem is that space has no mercy for imbalance. If energy in is too high, you cook. If energy out is too high, you freeze. If energy cannot move where it needs to go, one part fails while another part survives. If a system cannot adapt, the environment will not adapt for it. This idea becomes clearer when we look at planets. Mercury is close to the sun, yet its nights are extremely cold. It has almost no atmosphere to carry heat from day to night. The day side can bake under sunlight, while the night side loses energy into space. Being the closest planet to the Sun does not make Mercury uniformly warm. It makes sunlight intense and shadow severe. Venus is farther from the Sun than Mercury, yet it is hotter overall because it has a massive atmosphere and a powerful greenhouse effect. Its thick air traps and redistributes heat. The surface stays hot day and night. Venus teaches the opposite lesson. An atmosphere can matter more than simple distance. Earth sits between them, with oceans and air that moderate temperature. The Moon sits near us, but without our atmosphere, it swings violently. Mars sits farther out, with a thin atmosphere that cannot protect the surface the way Earth's does. The outer planets receive weak sunlight, but their atmospheres and internal heat create their own complexities. The solar system is a laboratory, showing that temperature is not just closer means hotter, farther means colder. It is atmosphere, rotation, surface, sunlight, internal heat, and energy balance. A human colony on any world would have to master that. On Mercury, living near the poles or in permanently shadowed craters might offer access to ice, but also severe cold. On the Moon, polar regions are attractive partly because of water ice and possible sunlight on high terrain, but the thermal geography is harsh. On Mars, habitats may need burial for radiation and temperature stability. On icy moons, the surface may be unimaginably cold, while subsurface oceans hide below. On a spacecraft, every wall must replace what a planet normally gives for free. Space settlement, therefore, is not just about getting somewhere, it is about bringing climate with us. A ship to Mars is a moving climate. A lunar base is an artificial climate. A station near the Sun is an artificial climate. A telescope behind a sunshield is an artificial cold world. A probe in the outer solar system is a small warm island powered by dwindling energy. This is the part of space exploration that is easy to miss, because rockets are louder. Launch is dramatic. Fire, smoke, acceleration, countdown, applause. But after launch, the quieter problems begin. Thermal systems run for years. They do not get applause every orbit. But without them, the mission ends. The universe is not conquered by launch alone. It is negotiated by temperature, hour after hour. And this brings us back to the original question. Why can space freeze you even near the Sun? Because the Sun does not warm space like a furnace warms a room. It sends radiation across a vacuum. If that radiation reaches you, it can heat you strongly. If it is blocked, reflected, or absent, your warmth can radiate away into a universe that gives little back. There is no thick air to hold the heat around you. No natural blanket. No gentle transfer. Only energy arriving, energy leaving, and the narrow survival range between. That is why a spacecraft can be hot and cold at once. That is why shadows on the Moon can preserve ice. That is why Mercury can have frozen darkness near the Sun. That is why deep space probes need heat. That is why astronauts need cooling and insulation at the same time. That is why the cold of space is not simple, but more dangerous than ordinary cold. Ordinary cold surrounds you. Space cold abandons you. It removes the environment your body understands and asks your equipment to replace it perfectly. For a while, technology can do that. A suit can hold pressure. A cabin can move heat. A shield can block sunlight. A heater can protect a valve. A radiator can release waste energy. A telescope can hide from the Sun and turn cold into vision. But all of those victories depend on design, power, orientation, maintenance, and time. The universe does not keep us warm. We keep ourselves warm. And sometimes, when we get too warm, we ask the universe to take that heat away. That is the strange bargain of space. The same darkness that can freeze a machine can save another one from overheating. The same sun that gives life to Earth can destroy exposed equipment. The same vacuum that makes cold deadly can preserve heat inside insulation. The same thermal sink that threatens a human body lets us build instruments sensitive enough to study ancient light. Space is not merely cold. It is a place where temperature stops being a background condition and becomes a mission. There is also a slower danger hidden inside this subject: thermal memory. Objects do not instantly become the temperature of their surroundings. A thick piece of metal can store heat. A tank full of liquid can resist change. A small exposed sensor can change quickly. A thin wire can cool faster than a massive engine. A human body has blood, water, organs, and metabolism. A spacecraft has compartments, insulation, structural paths, and internal power. Nothing simply snaps to one universal space temperature. This is why timing matters. A few minutes in shadow may be safe for one system and dangerous for another. A short eclipse may be planned into a mission. A long eclipse may become a crisis. A rover may survive a cold night if its batteries are charged and heaters are ready, but fail if dust has reduced solar power during the day. A lander may last through one thermal cycle and then weaken through the next. Repeated expansion and contraction can fatigue parts slowly, even when no single moment looks catastrophic. Space cold is often cumulative. It works through cycles: day, night, sunlight, shadow, warm-up, cool-down, expansion, contraction. A seal that survives once may not survive forever. A cable that flexes with temperature may eventually crack. A mirror that changes shape by a tiny fraction may blur an observation. A joint that becomes too cold may refuse to move at the one moment it is needed. Cold is not only a number on a scale, it is a stress placed on materials over time. This matters for anything that has to last. A short-lived probe can be built for a violent but brief environment. A long-lived observatory must remain stable for years. A base for humans must survive seasons, failures, repairs, mistakes, and normal use. The longer we stay in space, the less impressive a single survival event becomes. The real test is whether a system can keep repeating survival until survival becomes ordinary. That is much harder. Imagine a future ship traveling from Earth to Mars. It rotates slowly in cruise. Sunlight falls on one side. Radiators point away. Tanks are insulated. Computers are cooled. Crew quarters are warmed. Water is stored. Food is protected. The ship may look calm from the outside, but its thermal control system is constantly adjusting. Pumps move fluid. Sensors report temperatures. Software decides when to heat or cool. The crew sleeps because invisible loops are doing their work. Now remove one pump. The ship does not explode. It becomes less flexible. A backup takes over. Then another component runs warmer. A heater schedule changes. A valve is used more often. Power margin narrows. A mission that still looks healthy from the outside becomes more fragile on the inside. This is how many real engineering problems feel. Not like disaster immediately, but like a reduction in choices. Space punishes the loss of choices. That is why a thermal system is not only a support system, it is part of the mission's freedom. If a spacecraft can control temperature well, it can point instruments longer, enter shadows safely, survive eclipses, run experiments, and wait through unexpected conditions. If thermal margins are small, mission planners become cautious. Science windows shrink. Maneuvers are limited. Human work outside the vehicle becomes more dangerous. The environment has not changed, but the mission's ability to face it has. This is especially important for places that seem attractive because of one advantage. The moon's poles may offer ice and unusual sunlight patterns, but permanent shadow means severe cold. Peaks of near continuous light may help with power, but nearby craters may be thermally extreme. Mars offers a surface and resources, But dust, thin air, and cold nights complicate power and heating. Asteroids may contain valuable material, but their small size and rotation can create harsh temperature swings. Mercury has intense sunlight, but also deep shadow and long nights. Every promising place has a thermal price, and that price decides architecture. Do you build underground? Do you use nuclear power? Do you store heat in water, or molten salts or regolith? Do you place radiators high above dusty ground? Do you design suits for sunlight, shadow, or both? Do you send robots first to map temperatures before humans arrive? Do you accept a short mission or build for permanence? These questions may sound less exciting than landing sites and rockets, but they are what turn an idea into a base. A colony is not real because people land there once. A colony is real only if it can keep temperature, pressure, water, food, power, and repair cycles stable for years. Heat is the quiet thread running through all of it. Even the search for life is connected to temperature. Life as we know it needs liquid water, and liquid water needs pressure and temperature conditions that allow it to remain liquid. Too hot, and chemistry breaks down. Too cold, and reactions slow or water freezes. But under ice, near hydrothermal vents, inside rock, or beneath thick atmospheres, heat can be stored and shaped in unexpected ways. A world may look frozen from space while remaining active below. A moon far from the sunday may be warmed by tides. A planet close to a star may be protected by clouds or destroyed by runaway greenhouse heating. Once again, distance alone is not enough. The universe hides habitability inside heat flow. A frozen surface may not mean a dead world. A sunlit surface may not mean a living one. A cold moon may have an ocean. A warm planet may be sterile. A spacecraft may need both shade and heaters. The more we study space, the more the simple labels fail. Hot planet, cold space, near the sun, far from the sun, habitable zone, deep freeze. These words are useful only until the details arrive. Then the real story becomes energy. Where it enters, where it leaves, where it is trapped, where it is moved, and whether anything can use it before it disappears. That is why space cold is terrifying. In a calm way, it does not need monsters. It does not need speed. It does not need explosions. It only needs a warm object, a view of the dark, and enough time. Given enough time, an unpowered object radiates. Given enough distance, sunlight weakens. Given enough shadow, surfaces fall toward deep cold. Given enough failure, a protected cabin becomes a physics experiment. The danger is not loud, because radiation is silent. No wind screams as heat leaves. No frost has to form in the air. A spacecraft can cool in perfect silence, while every sensor number slowly moves in the wrong direction. That silence is part of what makes the subject feel so strange. On Earth, cold often announces itself. You see breath in the air. You hear wind. You feel snow. Pipes freeze and crack. Frost grows on windows. In space, the most important thermal changes can happen without sound, without weather, without visible ice. A panel radiates infrared into blackness. A battery temperature falls. A valve approaches its limit. A computer waits for a heater command. The universe remains visually beautiful while the margin disappears. This is why the cold of space is not just a temperature story. It is a design story, a survival story, a story about how fragile warmth really is when the planet is no longer helping. Part 1 of this journey begins with that physics. Radiation, shadow, vacuum, sunlight, spacecraft survival, and the fragile thermal balance that keeps humans and machines alive. But the story goes deeper, because once we understand why space can freeze you near the sun, we can begin asking something even stranger. What happens when we move farther from the sun? Into regions where sunlight fades, planets become colder, probes depend on tiny nuclear hearts, and the universe itself becomes the main thing a warm object must face. To answer that, we have to keep moving outward, away from Earth's orbit, past Mars, past Jupiter, past the last useful warmth of sunlight, toward the deep cold that waits between the worlds. The first deep cold is not reached at the edge of the galaxy. It begins much closer. It begins the moment sunlight stops being the easy answer. Near Earth, the sun is so bright that almost every spacecraft has to manage both heating and cooling at the same time. Solar panels collect power. Radiators throw waste heat away. Multi-layer insulation slows unwanted loss. Heaters protect valves, lines, and batteries when a surface falls into shadow. Even there, in the warm inner solar system, survival is already a balancing act. But as a spacecraft moves outward, the equation changes. The sun does not switch off. It fades by distance. At twice Earth's distance, the same surface receives only about 1/4 of the sunlight. At 5 times Earth's distance, near Jupiter, it receives only about 1/25. At 10 times Earth's distance, near Saturn, the light is roughly 100 times weaker than it is near Earth. That simple rule turns the solar system into a slow thermal staircase. Every step outward gives less incoming energy. Every step outward makes shadows easier to enter and harder to escape. This is where the cold becomes less dramatic, but more serious. A person standing outside on Earth feels the sun as immediate warmth. Move that same person to Mars inside a protective suit, and the sunlight is still visible, but it is not the same gift. Mars orbits farther from the sun, receives weaker sunlight, has a thin carbon dioxide atmosphere, and has surface temperatures that can fall far below anything humans can tolerate without protection. The sky can look bright. The ground can look dusty and solid. A robotic rover can cast a clean shadow on the soil. Yet the environment is still trying to drain heat from machines in ways that never happen on a mild day on Earth. Mars is important because it breaks another simple idea. A planet can be close enough to see the sun clearly and still be a cold trap for humans. A future Mars base would not only need oxygen and pressure, it would need constant temperature control. The habitat walls would have to slow heat loss during the night. The batteries would need protection through cold cycles. The water systems would have to avoid freezing in lines, filters, tanks, seals, and waste processors. Airlocks would become thermal stress points. Suits would leave a warm cabin, enter a freezing exterior, collect dust, return through a pressure chamber, and then repeat the process for months. On Mars, cold is not only outside, it tries to move into every system. A pump that works in a laboratory on Earth might fail if its lubricant thickens. A rubber seal might become stiff. A metal joint might shrink just enough to change a tolerance. An exposed cable might cycle between sunlight and night until its insulation cracks. A rover wheel can survive thousands of turns, then fail because repeated thermal changes slowly weakened one small part. The dangerous cold is not always a single deadly temperature. Sometimes it is the damage caused by crossing temperatures again and again. This is why a Mars colony is not simply a desert camp with pressure domes. It is a thermal machine. Every wall, pipe, window, radiator, heat exchanger, cable run, suit locker, and storage tank becomes part of the survival system. The colony has to hold warmth where humans need it, reject heat where equipment produces too much, and keep freezing from spreading through ordinary infrastructure. A greenhouse on Mars is not just a greenhouse. It is a fight between light, insulation, pressure, humidity, condensation, ice, and dust. A water tank is not just storage. It is thermal mass, radiation shielding, and a disaster waiting to happen if it freezes in the wrong place. Mars is still not the deep outer solar system. It is only the first lesson. Beyond Mars, the Sun begins to feel less like a local star and more like a distant lamp. Between Mars and Jupiter lies the asteroid belt, a wide region filled not with crowded rocks crashing everywhere, but with scattered worlds separated by enormous emptiness. Many of these bodies are dark, carbon-rich, metallic, icy, or dusty. Some rotate slowly, exposing one side to weak sunlight and then letting it cool into long darkness. On a small asteroid, there may be no atmosphere at all to share heat across the surface. One area faces the sun and warms. Another faces deep space and radiates away. A lander touching down on such a body does not find a stable outdoor temperature. It finds a surface controlled by shape, rotation, material, shadows, and how deeply heat can move into the ground. An asteroid is a small object, but thermally it can be complicated. Loose dust can insulate. Solid rock can conduct. Dark material can absorb sunlight efficiently. Bright material can reflect much of it. A boulder sitting on the surface may warm differently from the powder around it. A shadowed crack may hold cold longer than an open plain. A spacecraft trying to anchor, drill, sample, or fire a small thruster nearby has to understand those differences, because touching the surface is not only mechanical, it is thermal. If humans ever mine asteroids, the cold will not be background decoration. It will decide how machines are built. A drill entering a frozen body may heat the material around the bit and change what it is drilling into. Ice that was stable for millions of years may sublimate when exposed. A sample container may need to keep volatile material cold enough that it does not vanish before analysis. A refinery placed on a tiny body may need to trap heat carefully because there is no surrounding air to carry heat into the equipment. Waste heat can be a problem even in cold space, because if a machine has nowhere good to put it, it can overheat while the structure around it freezes. This contradiction keeps returning. Cold space does not mean every machine automatically becomes cold. A reactor can overheat in darkness. A computer can cook inside an insulated box. A telescope detector can need extreme cooling, while nearby electronics need warmth. A tank can freeze, while a processor beside it needs a radiator. Space thermal design is not about finding one temperature. It is about controlling many temperatures inside one object that is surrounded by vacuum. Then comes Jupiter. From Earth, Jupiter is a bright point in the night sky. Through a telescope, it becomes a striped giant, with storms larger than planets. But for a spacecraft arriving there, Jupiter is also a new thermal world. Sunlight is far weaker. The planet itself glows with infrared heat from inside, but that heat is not a comfortable blanket for a human vehicle. Jupiter is surrounded by radiation belts, moons, plasma, dust, shadow, and a complex magnetic environment. A spacecraft has to survive not only cold and weak sunlight, but also electronics damage and intense operational constraints. At Jupiter, solar power becomes harder, but not impossible. NASA's Juno spacecraft proved that solar panels can work at Jupiter, but they had to be large because the sunlight is so much weaker than it is near Earth. The deeper lesson is clear. As distance increases, a spacecraft must either carry huge collecting area, use less power, rely on nuclear energy, or accept shorter missions. The sun has not disappeared, but it no longer feels generous. Every watt becomes precious. Every heater competes with every instrument. Every thermal decision becomes part of the mission's lifetime. Now imagine a human ship at Jupiter. The view would be overwhelming. The giant planet would dominate the sky. Its moons would move like separate worlds. Europa would shine with ice. Io would glow with volcanic scars. Ganymede and Callisto would look like ancient frozen records of impacts and internal history. But inside the ship, the beauty would matter less than the numbers on the thermal panel. How much heat is the crew making? How much power can the system spare for heaters? Which fuel lines need warmth? Which instruments must be cooled? Which side of the ship is facing Jupiter's reflected light? Which side faces the sun? And which side sees only blackness? A place can be visually magnificent and operationally hostile. Europa makes the problem even sharper. From a distance, Europa looks like a bright, cracked moon covered in ice. Under that ice may be a deep ocean, warmed not mainly by sunlight, but by tidal forces as Jupiter's gravity flexes the moon. The surface can be brutally cold, while the interior may hold liquid water. That single world shows that heat in space does not have one source. Sunlight is only one part of the story. Gravity can become heat. Radioactive decay inside rock can become heat. Friction can become heat. Chemical reactions can matter. A moon can be frozen outside and active inside. This is not a contradiction either. It is a warning. If humans judge a place only by sunlight, they misunderstand it. Io, near Europa, gives the opposite example. It is the most volcanically active world in the solar system, heated by tidal flexing, not by being close to the sun. It erupts in a region where sunlight is weak compared with Earth. So the solar system contains both extremes in the same neighborhood: frozen surfaces, hidden oceans, volcanic fury, radiation belts, and deep shadow. Cold space is not simple emptiness. It is a landscape where energy hides in different forms. That matters for exploration, because humans cannot survive on appearance. A smooth, icy plain may hide an ocean. A dark crater may preserve ancient ice. A volcanic moon may be heated by gravity. A spacecraft behind a shield near the Sunday may need heaters. A rover on Mars may freeze under a dusty sky. The question is never only, how cold is it there? The better question is, where is the energy coming from? Where is it going? And can we control the path long enough to stay alive? Past Jupiter, the sun weakens again. At Saturn, the light is soft compared with Earth's daylight. It is still bright to human eyes because our eyes adapt, but the energy available per square meter is much lower. Saturn's rings shine in reflected sunlight. Its moons drift through a pale, distant glow. A spacecraft there sees beauty, but its power system sees arithmetic. Solar energy is possible with very large arrays, but many outer solar system missions have used radioisotope power because the sun cannot be trusted to deliver enough energy for every need. Titan, Saturn's largest moon, is one of the best examples of cold becoming almost Earth-like in shape, but alien in substance. Titan has an atmosphere. It has clouds. It has rivers, lakes, and seas. It has weather. But the liquid on its surface is not water. It is methane and ethane, stable in Titan's extreme cold. Water ice there behaves more like rock. The landscape can look familiar in outline, yet every physical rule feels shifted. A shoreline on Titan may look like a shoreline, but it exists at a temperature where human biology cannot function, and ordinary Earth materials would face a different chemical world. This is an important step in the journey. Cold does not only kill by freezing humans, it rewrites what counts as rock, liquid, air, and weather. On Earth, water flows. Nitrogen and oxygen fill the air. Methane is a gas, and ice is a temporary surface condition in many places. On Titan, water ice can form terrain. Methane can rain. Organic haze can tint the sky, and sunlight arrives as a weak orange glow filtered through atmosphere. A human base there would need to manage pressure, chemistry, cold, power, and isolation in a way unlike Mars or the Moon. It might be protected from some radiation by Titan's atmosphere. But the temperature problem would be relentless. A heater on Titan is not comfort, it is civilization. Without heat, instruments fail, seals change behavior, batteries weaken, fuels thicken, lubricants stiffen, and life support becomes fragile. A habitat would need insulation not just against a winter night, but against an entire world whose natural state is far below human survival. The outside air would not rush in as breathable atmosphere. It would be a cold chemical environment that could enter equipment, condense in the wrong places, and turn ordinary repair into a dangerous thermal operation. Farther still, Uranus and Neptune wait in dim blue distance. At those worlds, sunlight is a memory compared with Earth. Uranus orbits almost 20 times farther from the Sun than Earth. Neptune orbits about 30 times farther. The Sun seen from Neptune would still be brighter than other stars, but it would not dominate the sky the way it does for us. For a spacecraft there, solar panels become impractical for many serious missions, and thermal power becomes a problem of endurance. Neptune is especially strange because it radiates more energy than it receives from the Sun. That internal heat helps drive winds and weather in a place where sunlight is weak. Again, the solar system refuses to be simple. A planet can be far from the Sun and still dynamic. It can be cold at cloud tops and energetic inside. It can move storms through an atmosphere where the Sun contributes only a small part of the available power. For humans, though, this does not make the environment friendly. There is no surface to stand on at Neptune. There is no easy refueling station. There is no quick rescue. A crewed mission there would be a moving world of its own, carrying warmth, power, spare parts, shielding, food, and medical support for years. Thermal control would not be one system among many. It would be tied to everything: propulsion, radiation shielding, habitation, air recycling, water recycling, electronics, medicine, agriculture, and crew psychology. A cold spacecraft is not just uncomfortable, it becomes unreliable. A frozen valve can trap propellant. A cold battery can lose capacity. A chilled chemical process can slow until life support falls behind demand. Condensation can form where moisture touches a cold surface inside a habitat. Ice can grow in places that were never meant to hold it. Sensors can drift. Displays can fail. Adhesives can crack. Flexible parts can become brittle. A single thermal blind spot can become a mission-ending weakness. This is why deep space missions often look strange to people outside engineering. They are wrapped in gold-colored insulation. They carry radioisotope heaters. They use louvers, radiators, coatings, blankets, thermal straps, electric heaters, and careful orientation. They rotate sometimes not for drama, but to distribute heat. They shut down instruments sometimes not because science is over, but because power and temperature margins have changed. They may keep one component warm while allowing another to cool. They may point a dish, a shield, a radiator, and a solar array in different directions, because thermal survival and communication have to share the same vehicle. The farther from the Sun we go, the more the ship must become its own climate. That is one of the most important truths of human spaceflight. Earth is a climate we inherited. A spacecraft is a climate we must build. When we talk about traveling through cold space, we often imagine the danger outside the window, but the more practical danger may be inside the walls. A human cabin is warm, wet, chemical, electrical, and biological. Humans breathe water vapor into the air. They sweat, they cook, they wash, they use electronics, they store food, they move heat from their bodies into the cabin. All of that has to be controlled in a sealed environment. If part of the hull becomes too cold, moisture can condense there. If it becomes colder, it can freeze. If hidden areas collect ice, the problem may not be seen until it affects airflow, insulation, wiring, or structural panels. Cold can create water where water should not be. That sounds strange, but it is familiar on Earth. A cold window gathers condensation in a warm room. In a spacecraft, the same idea becomes more serious. Moisture has nowhere natural to go. Airflow must guide it. Dehumidifiers must collect it. Surfaces must stay above certain temperatures. If the thermal system fails, the cabin can develop local problems before the crew feels general cold. A habitat can have warm people and cold walls. That is dangerous. Food storage creates another thermal puzzle. Some items need freezing, some need refrigeration, some need dry storage. Some medical supplies need narrow temperature ranges. Seeds may need protection from heat, cold, and radiation. Biological samples may need cold preservation, but not uncontrolled freezing. A deep space colony cannot simply place everything outside and call it a freezer. Space is not a neat refrigerator. Direct sunlight can overheat exposed containers. Shadows can overcool them. Vacuum can remove volatile material. Radiation can damage organics. Thermal cycling can break packaging. Even waste has a temperature problem. Human waste contains water, salts, organic material, and potential resources. A long mission may need to recycle as much as possible. If waste lines freeze, they become more than a plumbing issue. If recycling systems fall outside their operating temperatures, water recovery can fail. If a biological processor becomes too cold, microbes can slow or die. If a chemical reactor becomes too warm, it may become unsafe. The cold outside cannot be separated from the life support inside. That is why the real horror of space cold is administrative as much as physical. It turns ordinary maintenance into survival. A loose connector is not just a loose connector if it controls a heater. A delayed software update is not just annoying if it changes thermal cycling. A dusty radiator is not just dirty if it cannot reject heat. A blocked vent is not just inefficient if condensation begins behind a panel. A tiny design assumption made on Earth can become a crisis millions of kilometers away. Then we reach the Kuiper Belt. This is the broad region beyond Neptune where icy bodies, dwarf planets, and ancient debris orbit in the weak outer light of the Sun. Pluto is the most famous of these worlds, but it is not alone. There are many distant objects, some known, many still faint and difficult to study. Out there, sunlight is so weak that noon would not feel like noon on Earth. It would feel like a dim twilight, and yet to human eyes, the Sun would still be a special star, far brighter than the others. Pluto shows how cold changes a world over time. When New Horizons flew past Pluto, it revealed mountains of water ice, plains of nitrogen ice, hazes, glaciers, and a world more active than many expected. The surface was not simply dead. It had features shaped by volatile ices at temperatures unimaginable for Earth-like life. Nitrogen, methane, and carbon monoxide can behave there in ways that require extreme cold. A small amount of sunlight, internal heat, seasonal changes, and surface chemistry can still produce geology. This is another important correction. Cold does not mean nothing happens. It means different things happen slowly, with different materials, under different rules. On Pluto, water ice is hard enough to act like bedrock. Nitrogen ice can move. Thin atmosphere can appear and change with distance from the Sun. Frost can migrate over long seasons. The landscape is not warm, but it is not meaningless. It is a record of how cold worlds process energy across enormous time. For explorers, though, that beauty would be almost useless for comfort. A base on Pluto would need nearly all its practical energy from carried or locally built power systems. Solar power would be extremely weak. A habitat would need to hold heat with extreme efficiency. Rovers would need energy sources that do not depend on daily sunlight. Surface operations would be slow, careful, and dangerous. A punctured suit or failed heater would not be a temporary emergency. It would be fatal unless redundancy worked immediately. At Pluto, the Sun is still there. Beyond Pluto, the solar system becomes even less familiar. A comet in the outer darkness can remain frozen for vast stretches of time. Far from the Sun, its ices sit quietly. The nucleus may look like a dark, irregular rock, but much of its story is locked in frozen, volatile material. Then, if its orbit carries it inward, sunlight grows stronger, ice sublimates, gas escapes, dust lifts away, a coma forms, a tail grows. The object that slept in cold for ages becomes visible, because heat finally reaches it. Comets are messages from the cold. They show that freezing is not only destruction. Sometimes it is preservation. The outer solar system has preserved ancient material because the cold slowed change. Molecules that would not survive long on warmer worlds can remain trapped in ice. Dust and chemistry from the early solar system can be stored in dark reservoirs. When a comet falls inward, it carries that frozen record toward the Sun. Its tail is not just beautiful. It is material released from a cold archive. That archive matters because the cold regions of the solar system may hold clues about how planets formed, how water and organics moved, and how Earth received some of the ingredients needed for life. The deep cold can erase activity, but it can also protect information. This is why scientists value samples from comets and asteroids. They are not just rocks, they are pieces of a colder past. Yet preservation does not make the environment gentle. A spacecraft near a comet has to survive dust, gas jets, weak gravity, uneven illumination, and extreme surface temperatures. It may need to keep instruments warm while measuring cold material. It may need to collect samples without heating them too much. It may need to avoid contaminating the very chemistry it came to study. Again, the thermal problem is not just whether the place is cold, it is how to keep each part of the mission at the right temperature while interacting with a world that is changing. Now move even farther, toward the edge of the Sun's influence. The heliosphere is the bubble carved by the solar wind as it pushes into the surrounding interstellar medium. Inside it, the Sun still shapes the environment through charged particles and magnetic fields. Outside it, spacecraft enter interstellar space, though they are still much closer to the Sun than to any other star. Voyager 1 and Voyager 2 have crossed into this region, becoming humanity's most distant messengers. For Voyager, cold is not a dramatic cinematic threat. It is a slow power budget. The Voyagers carry radioisotope thermoelectric generators, devices that turn heat from radioactive decay into electricity. Over time, the available power decreases. As power drops, engineers have to choose which instruments and heaters can remain on. A spacecraft can be physically healthy in many ways, but still face the end of its mission because it no longer has enough power to keep systems operating. That is a different kind of freezing, not instant ice, not a body turning solid in seconds. A slow narrowing of options. A heater stays off. An instrument cools. A system is disabled to save power for communication. The spacecraft continues moving, but its working life becomes smaller. The cold of deep space is not only the background temperature, it is the fact that warmth costs energy, and energy is finite. For a human mission, this would be far more severe. Humans cannot be shut down like instruments. A crew needs heat, air circulation, water recycling, food production, medical systems, lighting, computing, exercise equipment, waste handling, and psychological stability. Each of these produces or requires heat. Each depends on power. If power declines, the crew cannot simply turn off the habitat for a decade and coast. They must remain within a narrow living range every day. A robot can sleep through parts of deep space. A human world cannot. This is why deep cold forces the question of energy before almost anything else. What powers the mission when the sun is too weak? Chemical fuel is not enough for centuries. Batteries store energy, but do not create it. Solar power becomes weaker with distance. Nuclear fission could provide steady power if engineered safely and maintained. Fusion is still not a routine, practical spacecraft power source. Radioisotope systems can run for long periods, but produce limited power. Beamed energy may work in some imagined architectures, but the farther the ship goes, the harder alignment, distance, and infrastructure become. A starship is not mainly a fast engine. It is a portable energy economy. It needs enough power to move, enough power to live, enough power to repair itself, enough power to stay warm, and enough power to get rid of excess heat. That last part sounds strange after so much cold, but it never goes away. A nuclear-powered ship in deep space may still have to reject large amounts of waste heat. It may need enormous radiators, and those radiators must face cold space to work. If they are damaged, the ship can overheat in a region where the universe is almost freezing. This is one of the most important paradoxes. Deep space can freeze you, but a powerful spacecraft can still die from overheating. The environment is cold, but there is no air to carry heat away. A reactor, engine, or life support plant produces heat internally. That heat has to be moved to radiators and emitted as infrared light. If the radiators are too small, too damaged, badly oriented, coated with dust, or folded away for protection, the interior can become unsafe. So a deep space vessel needs both heaters and coolers, insulation and radiators, heat storage and heat rejection. The ship is not fighting cold alone. It is fighting imbalance. Near the sun, imbalance can mean one side burns and another side freezes. Far from the sun, imbalance can mean life support equipment makes too much heat, while external tanks need protection from freezing. On an icy moon, imbalance can mean a drill melts the material it needs to sample. On a generation ship, imbalance can mean agriculture, humans, computers, reactors, and radiators all pulling the habitat into different thermal needs. This is why the idea of cold space must be separated from the idea of simple cold. Space is not a freezer with stars inside. It is a thermal vacuum where objects become responsible for their own energy balance. If the balance fails, heat moves the only ways it can: through solid connections, through fluids inside pipes, through radiation into darkness, through sunlight when sunlight is available, through internal power when power exists, through stored heat until storage runs out. This is where human imagination often goes wrong. We picture the astronaut floating in space and freezing instantly, like something dropped into liquid nitrogen. Real exposure to vacuum is more complex and dangerous for several reasons, especially pressure loss and lack of oxygen. But freezing is not usually the first instant effect. Heat leaves by radiation, and radiation takes time. The bigger immediate dangers include ebulism, hypoxia, tissue damage, and the failure of the body to operate without pressure. But if a body or suit remains exposed and unheated, cold becomes part of the longer fatal environment. This difference matters because it shows how strange the vacuum really is. You do not freeze because icy air surrounds you. You freeze because your heat has no reliable replacement. A spacesuit solves this not by being a coat alone, but by being a small spacecraft. It provides pressure, oxygen, carbon dioxide removal, cooling, heating, insulation, communications, and sometimes active liquid cooling close to the body. Astronauts can actually overheat inside a suit because the body generates heat and the vacuum does not remove it like wind would. The suit has to carry heat away through controlled systems. In shadow or during long operations, it also has to prevent dangerous cooling of components and body areas. The human body is a heat engine. It makes heat constantly. On Earth, the environment helps remove it. Air carries it away. Sweat evaporates. Clothing adjusts heat flow. Shade and wind matter. In a spacesuit, all of that becomes engineered. If the cooling system fails, the astronaut may overheat. If heating and insulation fail in cold conditions, parts of the system can cool dangerously. The same suit must avoid both extremes, because space does not gently regulate either direction. That is why a spacecraft cabin is more like a living thermos than a room. It has to keep heat from escaping too fast, but also remove heat from people and equipment. It has to circulate air, so warm and cold pockets do not form. It has to recover water vapor. It has to keep windows from becoming thermal weak points. It has to prevent condensation. It has to protect storage. It has to survive sunlight, eclipse, maneuvers, docking, shadow, and hardware changes. Even a short journey to the moon shows this. A vehicle in Earth orbit passes in and out of sunlight. In sunlight, surfaces heat. In Earth's shadow, they cool. The cycle repeats many times. A lunar mission faces long exposure to space, then a landing environment where dust, sunlight, shade, surface reflection, and local terrain all affect thermal behavior. A Mars mission faces months of cruise, then entry, descent, surface operations, dust accumulation, and seasonal changes. Each mission is not one environment. It is a sequence of thermal environments. The farther humans go, the longer the sequence becomes. A mission to Jupiter's moons would involve inner solar system departure, deep cruise, changing solar power, radiation protection, orbit insertion, moon flybys, eclipses, and possibly landing. A mission to Saturn would face even weaker sunlight, colder target worlds, longer communication delays, and greater dependence on long-lived power. A mission to the Kuiper Belt would require almost complete independence from solar energy. An interstellar mission would leave even the outer planets behind and carry its thermal civilization into a darkness where the sun no longer feels like a source of survival. In interstellar space, the most famous temperature is the cosmic microwave background. It is the afterglow of the early universe, now cooled to only a few degrees above absolute zero. That does not mean every object instantly becomes that temperature, because objects have internal heat, starlight, cosmic rays, dust interactions, and their own radiation balance. But it tells us something profound. Once you move far from stars and planets, the universe itself offers only a faint thermal background. It is not warm enough for life, machines, or chemistry as we know them. It is a thin whisper of ancient heat spread across the sky. A dark object floating far from any star, with no internal power, would slowly radiate away energy until it approached an equilibrium with the weak radiation around it. That is the final cold waiting behind the local examples, not the shadow of a spacecraft near Earth, not the night side of the moon, not a Martian winter, not the surface of Pluto, but the deep background of the universe, where warmth must come from inside or from distant stars. This is why stars matter so much. A star is not only a light in the sky, it is a local interruption in cosmic cold. It pours energy into space, and any object near it has to decide what to do with that energy. Too close, and the energy can destroy. Too far, and it becomes too weak to help. The habitable zone around a star is partly a thermal idea, a range where a planet with the right atmosphere might maintain liquid water on its surface. But even that phrase can mislead. A planet's temperature depends on atmosphere, clouds, albedo, rotation, oceans, greenhouse gases, internal heat, orbit, and many other details. Earth is not comfortable only because of distance. It is comfortable because many systems work together. Atmosphere spreads heat, oceans store and move it, Clouds reflect and trap radiation. Greenhouse gases keep the surface warmer than it would otherwise be. The rotation of the planet creates day and night cycles that the climate can survive. The surface, air, and water exchange energy constantly. Life itself participates. Earth is not simply sitting in the right place. It is a world with a working thermal partnership. Remove that partnership, and the same sunlight can become hostile. The Moon receives almost the same sunlight as Earth, but has brutal surface swings. Mars receives weaker sunlight and has a thin atmosphere that cannot provide Earth-like warmth. Venus receives strong sunlight, but is dominated by a massive greenhouse atmosphere. Mercury is close to the Sun, but has extreme contrasts because it lacks a thick atmosphere. Titan is far away, but has a thick atmosphere and methane weather in extreme cold. Europa is frozen outside, but may be warm enough inside to keep an ocean. These examples show that space cold is not one number. It is the result of systems. For a human civilization leaving Earth, that lesson is terrifying, because it means we do not just need to travel, we need to recreate a system. A moon base needs buried habitats, insulation, power storage, thermal regulation, dust control, radiation shielding, and water management. A Mars settlement needs greenhouses, nuclear or solar energy, dust-resistant radiators, backup heaters, pressure-safe structures, and repairable life support. A spacecraft needs active thermal loops, backup pumps, spare valves, reliable sensors, and materials that can survive cycling. A deep space colony ship needs not only walls and engines, but an artificial climate that can be maintained for generations. Colonizing space is not simply bringing humans to new places. It is bringing controlled warmth into places that do not care if warmth exists. That may sound simple until you think about scale. Earth's biosphere is enormous. It contains oceans, air currents, soil, clouds, forests, ice sheets, and geologic cycles. It smooths changes, absorbs shocks, and gives life countless buffers. A spacecraft or habitat has almost none of that natural depth. It may have tanks, pumps, filters, radiators, batteries, reactors, greenhouses, and software. Those systems may be brilliant, but they are also narrow. If one breaks, there may be no forest, ocean, or atmosphere to help. The cold outside makes the inside more precious. A warm room in space is not just architecture. It is an act of resistance against the universe's default condition. Think of a cup of water in a spacecraft. On Earth, a cup of water is ordinary. On a deep space ship, it is pressure, temperature, containment, recycling, mass, biology, and risk. If released, it does not behave like spilled water on a kitchen floor. In vacuum, it can boil, freeze, evaporate, scatter, and coat surfaces depending on conditions. If kept inside, it must remain within safe temperatures, free of contamination, and part of a recycling system. The colder the surrounding environment, the more every fluid line becomes critical. Water is life. But in space, water is also a thermal material. It stores heat, it can shield radiation, it can freeze and expand. It can move energy through loops. It can condense on cold surfaces. It can become ice where ice is useful, or ice where ice is fatal. A mission that misunderstands water's thermal behavior may lose more than comfort. It may lose the ability to drink, cool equipment, grow food, or breathe through oxygen production. Air is similar. Air in a habitat is not just something to breathe. It carries heat from bodies and machines. It prevents hot and cold pockets. It moves moisture. It allows filters and sensors to sample the cabin. If fans fail, the air can become uneven. Carbon dioxide can collect. Humidity can rise in one region. Cold surfaces can gather condensation. Warm electronics can overheat, while another part of the cabin becomes too cold. On Earth, Gravity and convection help air circulate naturally. In microgravity, airflow must be designed. This is why thermal control is tied to almost every hidden system. You cannot separate heat from pressure. You cannot separate pressure from air. You cannot separate air from moisture. You cannot separate moisture from condensation. You cannot separate condensation from electronics. You cannot separate electronics from power. You cannot separate power from heaters and radiators. The chain is long, and cold attacks the weak links. Now imagine the ship suffers a partial power failure far from the sun. The lights do not all go out at once. That would be too simple. Instead, the crew sees a warning on one thermal loop. A backup pump comes online. A heater zone is reduced. A storage module is closed to save energy. A radiator angle is changed. The crew stops a science operation because it produces too much waste heat in the wrong place. Later, a water line approaches its lower limit. A battery warms slowly because it cannot be charged cold. An air duct begins to collect moisture. The problem is not cinematic, it is procedural. Procedural danger is harder to dramatize, but it is how missions die. A checklist becomes survival. A temperature graph becomes a map of the future. A heater that draws only a small amount of power becomes more important than a window full of stars. This is the version of cold that space documentaries often miss. The universe does not need to freeze a person instantly to be deadly. It only has to make every ordinary system require engineering. It only has to make warmth expensive. It only has to make mistakes difficult to repair. It only has to make the safe range narrow and the outside environment patient. The outside environment can wait forever. Humans cannot. Cold is also the reason some of our most powerful observatories have to be built like thermal puzzles. An infrared telescope cannot simply look at the universe while glowing warmly itself. If its mirrors, instruments, or support structures are too warm, they emit infrared radiation of their own. That internal glow can drown out the faint heat coming from distant stars, young planets, dust clouds, and galaxies. To see cool objects, the telescope must often be kept cold. It has to reduce its own thermal noise before it can listen to the quiet infrared universe. This turns cold from an enemy into a tool. A telescope does not want human comfort. It wants silence in infrared. That is why space observatories use shields, radiators, special orbits, cryocoolers, and careful instrument design. They separate hot sides from cold sides. They block sunlight, earthlight, and reflected heat. They let selected surfaces radiate into space. They place sensitive detectors where the thermal environment is stable. The goal is not only to survive cold, but to use cold as part of the instrument. The James Webb Space Telescope makes this idea easy to picture. It carries a large sun shield that keeps sunlight, Earth, and Moon on one side, while the telescope optics and instruments operate on the cold side. The shield is not decoration. It is the reason the observatory can see the infrared universe so clearly. One side faces warmth and power. The other side faces deep space and controlled cold. Between them is a carefully designed boundary, because a little unwanted heat can become noise. This is one of the clearest examples of the same rule. The sun is nearby. The telescope is still cold, not because the sun is weak, but because the telescope is protected from it. Cold, in that case, becomes a window. The cold side of a space telescope is not simply a frozen surface. It is a carefully maintained condition that allows ancient light to be detected. Some of the universe's most distant galaxies reach us stretched into infrared wavelengths. Dusty star-forming regions glow in infrared. Cool planets and brown dwarfs reveal themselves through heat more than visible light. If the observatory itself were too warm, It would be like trying to hear a whisper while standing beside a running engine. So the same environment that threatens astronauts also helps astronomers. Space is dangerous because it drains warmth. Space is useful because it can accept heat from instruments and let them become quiet. That dual nature is everywhere. A cryogenic fuel tank needs insulation because its contents must stay extremely cold. Liquid hydrogen and liquid oxygen can store enormous chemical energy for rockets, but they are difficult to keep. Heat leaks into tanks, propellant can boil off, pressure can rise. Valves, vents, shields, and tank materials all become part of the thermal story. Keeping something cold is not free, even in space, because sunlight, electronics, engines, and nearby structures can add heat. Keeping something warm is not free either, because radiators, shadows, and vacuum can take heat away. A spacecraft carrying cryogenic propellant is therefore fighting on both sides. It may want one tank cold enough to preserve fuel. It may want crew spaces warm enough for life. It may want engines protected from freezing. It may want electronics cooled. It may want batteries warmed. It may want a telescope instrument colder than the surrounding structure. All of this can happen on the same vehicle. That is why simple descriptions fail. There is no single spacecraft temperature. There is a map of temperatures. Some points are safe, some are too hot, some are too cold, some are changing too quickly. Some are stable now, but dangerous later. Engineers have to read that map before launch, during cruise, during maneuvers, during eclipses, during science operations, and during emergencies. The map changes with distance from the sun, spacecraft attitude, power mode, instrument use, dust, aging materials, and mechanical wear. Thermal cycling adds another hidden danger. Even if a system never reaches a single catastrophic temperature, repeated expansion and contraction can slowly damage it. Metals expand when heated and contract when cooled. Different materials change by different amounts. A bonded joint between two materials may experience stress every time the spacecraft enters sunlight or shadow. A circuit board can flex by microscopic amounts. A solder joint can fatigue. A mirror can shift alignment. A seal can become less reliable. A fuel line can experience strain at mounting points. The environment does not need to break something today. It can weaken it for years. This matters for missions that are supposed to last long beyond their original design. A spacecraft may survive thousands of thermal cycles before one old component stops behaving as expected. A rover may operate through many cold nights before a heater becomes less effective. A probe may pass through shadow events, engine firings, instrument warm-ups, and long quiet periods until the accumulated stress becomes part of its aging. Cold is therefore not only a place, it is a history written into materials. Every time a spacecraft warms and cools, it remembers in small physical ways. Insulation can degrade, coatings can darken or change. Radiators can become less efficient. Moving parts can experience different friction. Lubricants can migrate or thicken. Measurements can become less trustworthy. The mission that begins with clean margins can become more fragile after years of exposure. This is one reason old spacecraft are so impressive. They are not just surviving distance. They are surviving time. Time in vacuum, time in radiation, time through heating and cooling cycles, time with declining power, time with no repair crew, time while engineers on Earth learn to operate hardware that was built by people who may no longer be working on the mission. An old spacecraft sending one more signal from deep space is not a simple miracle. It is thermal engineering still holding together after decades. The same challenge would face any future human settlement. A colony does not only need equipment that works on day one, it needs equipment that still works after years of dust, radiation, thermal cycling, repair, replacement, and human error. A heater cable installed inside a wall may become important 10 years later. A radiator panel scratched by debris may reduce capacity. An insulation layer damaged during maintenance may create a cold spot that slowly causes condensation. A poorly routed pipe may be safe in one season and dangerous in another. When humans live somewhere permanently, thermal design becomes urban planning. Where do the warm modules go? Where are the cold storage areas? Where can radiators see the sky? Where will dust collect? How will repair crews reach frozen valves? How do you expand a base without creating new thermal weak points? How do you keep a hospital, greenhouse, workshop, habitat, reactor and storage yard at different temperatures in a vacuum or thin atmosphere? These questions sound less exciting than rockets, but they may decide whether the colony lives. A city on Earth can waste heat into the atmosphere, draw warmth from fuel, rely on buried pipes, and survive local failures because the environment is forgiving compared with space. A lunar city, Martian settlement, or outer moon base cannot treat heat as a background detail. Heat would be currency. It would be planned, moved, stored, reused, rejected, measured, and protected. Even human schedules would be shaped by it. On the moon, surface operations may avoid certain sun angles because equipment overheats or shadows become too dangerous. On Mars, rover routes may depend on battery temperature and seasonal dust. On Titan, machinery may need warm-up periods before work begins. In orbit, spacewalks may be planned around sunlight, shadow, and suit cooling capacity. In deep space, science operations may be scheduled according to power and thermal limits, not human curiosity. The universe does not care what time the crew wants to begin. The temperature margins decide. This is also why the phrase "near the sun" is so unsettling. Because even near a star, protection is not automatic. Near the sun, a spacecraft may need a heat shield to survive sunlight, while components behind that shield need carefully controlled warmth. If they become too cold, they fail. If they become too hot, they fail. Parker Solar Probe can fly through an extremely hot solar environment because its heat shield faces the sun and protects the rest of the spacecraft. But that success is not proof that space is warm. It is proof that temperature, particle density, sunlight, materials, orientation, and engineering are different parts of one problem. The corona can be extremely hot in terms of particle energy, while the particles are so sparse that they do not transfer heat like dense air would. That is a crucial distinction. Temperature and heat are not the same thing. Temperature describes the average energy of particles in a material or gas. Heat transfer depends on how much energy actually moves into or out of an object. A thin gas can have very high temperature but contain relatively few particles to collide with a spacecraft. Direct sunlight can deliver intense, radiant energy. A shadow can remove that input. A heat shield can block radiation. A radiator can emit infrared energy. A blanket can slow energy flow. These details decide survival more than a single dramatic number. So when someone asks, "How cold is space?" the careful answer is not one sentence. Space can be colder than any winter. Space can overheat a spacecraft. Space can preserve ice for billions of years. Space can let a comet sleep, then wake it near the sun. Space can freeze a line, while a computer beside it needs cooling. Space can make a shadow near a bright star more dangerous than a cloudy night on Earth. The terrifying truth is not that space is simply cold. The terrifying truth is that space is indifferent to balance. Earth gives us balance for free most of the time. We stand under an atmosphere that blocks radiation, spreads heat, traps warmth, supports pressure, and carries sound. We sleep in rooms where air touches our skin. We walk through environments where heat moves constantly, through conduction, convection, radiation, evaporation, and weather. We rarely have to think about the fact that we are warm objects in a cold universe, because our planet does the thinking for us. In space, every part of that protection becomes a machine, and every machine can fail. That is why a future astronaut near Mars, Jupiter, Saturn, or even close to the Sun is never just exploring a location. They are living inside a temporary agreement between physics and engineering. The agreement says that pumps will move fluids, heaters will activate, radiators will reject heat, insulation will hold margins, batteries will stay warm, suits will circulate coolant, software will respond correctly, and power will remain available. If the agreement holds, humans can cross enormous distances. If it breaks, the universe does not become angry. It simply becomes itself again. Silent, vacuum, radiation, darkness, cold where warmth is not supplied, heat where heat cannot escape. This is the environment waiting behind every dream of spaceflight. It is there on the shadowed side of the moon. It is there inside a dusty Martian night. It is there around icy moons, comet nuclei, frozen dwarf planets, and old spacecraft fading beyond the planets. It is there, near the sun, behind a shield, where one surface can face fire while another needs protection from cooling. And it is there in the deepest spaces between stars, where the background glow of the universe is only a few degrees above absolute zero. The story began with a contradiction. How can space freeze you even near the sun? The answer is that the sun does not warm emptiness the way a fire warms a room. It sends energy across vacuum until that energy hits something. After that, everything depends on surfaces, shadows, materials, orientation, power, radiation, internal heat, and time. Near the sun, you can burn. In shadow, you can cool. Inside a suit, you can overheat. Without power, you can freeze. Inside a spacecraft, one component can need a heater, while another needs a radiator. On a planet, an atmosphere can smooth the difference or make it worse. On an icy moon, the surface can be frozen, while an ocean hides below. In the outer solar system, cold can preserve ancient chemistry. In interstellar space, warmth becomes something a machine must carry for itself. This is why space is not just a place we travel through. It is a test of whether we can carry Earth-like conditions into places where Earth-like conditions do not naturally exist. Every successful mission is a small answer. Every probe that survives an eclipse. Every rover that wakes after a cold night. Every spacecraft that keeps a battery above its limit. Every astronaut who returns from a spacewalk. Every deep space signal from a fading machine tells us the same thing. We can survive the cold of space only by understanding that it is not one enemy. It is absence. It is exposure. It is imbalance. It is time. It is the slow escape of energy from anything warm enough to be alive. And that is what makes the cold near the sun so strange. Not that the sun fails to shine, but that shining is not enough by itself. A star can fill the solar system with light, and still the darkness beside that light can be deadly. A spacecraft can fly close to the sun and still need careful protection against both heat and cold. A human can look at sunlight in space and understand that warmth is not guaranteed. It has to be managed, it has to be powered, it has to be protected, it has to be earned. That is the real lesson hidden in the vacuum. Space can freeze you even near the sun, because space does not give warmth freely. It only allows warmth to last when something is built well enough to hold it.